Thank you very much, cool beer. And first of all, I like to thank you a lot for organizing this series. It's really exciting that we get back to this and that we have it in presence. So welcome everybody. I should admit right up front that I'm not a theorist. I'm an experimentalist. I'm thrilled and excited to be here. But the way that I'm presenting will be more of an attempt to advocate the need of complementary theoretical approaches and also demonstration of how little we can achieve if we don't have these complementary techniques. Yes, that's probably anticipating a bit the conclusions here, but this has been something I was always fully aware of, that my own capabilities in theory, especially in computational physics, are very limited. We do some of this, and I'm glad that today we also have Alexandre Merlin here from Toulon University, who collaborates with me in that matter. And so this work's been partially done in collaboration. So Alexander is here. This was to large parts the work of, Azam, who is at the moment visiting professor in Munich in Germany, Maria, who is in the audience, Mohamed Bakhbidar, Andreas Ruediger, and here from within Gitanjali, who is now Canadian Research Chair at McMaster, and François Legaré from INRS. So, as the title suggests, we do some simulation, and this is going to be on vibrational spectroscopy. So the first thing you should ask yourself, or can ask yourself, is why would anybody care? So this is a material science department, and why does symmetry matter? And some of you had the bad fortune of attending my classes, and well, it's not totally off. So in principle, material properties depend on symmetry to some extent, and especially those which are represented by odd rank tensors. Some of you carried you through that. Actually rely on the absence of an inversion symmetry. And to just remind you of some of those, there is no pyroelectricity and no electrocaloric effect, which is the change of the electric polarization dipole moment under changing temperature, which is in all motion detection systems. If you have a center of inversion symmetry, it doesn't work. The other way around, electrocaloric, a bit more recent conversion of electric fields into changes of entropy. So the other one, a little bit better known here, is second harmonic generation, which also relies on the absence of inversion symmetry. And I'm going to use that in a moment. Then, of course, piezoelectricity, which is probably the industrially most relevant ones. Actuators, injection valves, and engines, and so on, they're all piezoelectric. And this is a kind of a renaissance in that research field due to the fact that a lot of the commercially available piezoelectrics are lead-based. And now the research in this field is sort of relaunched 40 years after people thought it was already concluded, because lead is now to be removed from the market. So this is taking steam again here. The bulk photovoltaic effect. So for energy conversion, this is an effect that you can consider like the nonlinear extension of Ohm's law, but at high frequencies, optical frequencies, it essentially gives you an electric current under illumination without a need for any kind of interface or PN junction. It's a bulk effect. And something that some of you may, or most of you probably haven't heard about, is flexoelectricity. So the moment that you take a centrosymmetric material and you bend it, you ever so slightly, as long as you stay in the elastic regime, ever so slightly change the symmetry. And you know, when you bend something, the outer side gets slightly extended, the inner side gets slightly compressed, you get strain gradients, and you can show from thermodynamical considerations that this gives rise to polarization. So these things don't exist if your material is centrosymmetric. Now, this is an early example from 2006, a Nature paper where they used silicon, and they actually grew a little bit of extra, I think it was germanium on the top of the silicon, getting this wedge shaped, and this strain gradient and the broken inversion symmetry in this cross section essentially give rise to optical birefringence, electro-optic effects, and so on. So this was an early example of strain engineering to invoke new properties in materials. So There is a large variety of industrially relevant materials that are centrosymmetric. This is certainly not a comprehensive list, and I'm deliberately sticking to non-metals. But even metals recently came into focus due to spin polarized charge transport that may occur due to magnetic ordering if you lose centrosymmetry. So silicon, germanium, the classical semiconductors, stuff that we work with, titanium dioxide, strontium titanate, and so on. And wouldn't it be nice, well, this is the long-term goal, this is like a letter to Santa, wouldn't it be nice if we could engineer the strain in these materials to provoke new properties, to induce new properties that have an interest, so that are functional, and we know how to integrate them, we know all the processing for them, everything's established, so that would be nice. The midterm goal is a little bit more realistic, is let's try for ways to break this inversion symmetry. There's multiple ways. I said bending, strain from the substrate. There's other options which I'm going to describe in a moment. And probably the short-term goal is, let's see if we find broken inversion symmetry somewhere already and see what tools we have to figure it out before we can use it. So this is maybe less of a letter to Santa. This is a wish list to my PhD students, probably. So this is the outline of the presentation, and I'll briefly recollect Raman spectroscopy and why we chose this as compared to X-ray diffraction as a tool. And I'm coming to the theoretical part later, but again, this is how do we break inversion symmetry in a brute force approach? Nano annotations, poking into our samples, poking holes in there. The next thing is misfit dislocations that kind of occur spontaneously at interfaces, atomic steps. This will be discussed on strontium titanate, and then I shift to magnesium oxide. And this is an expression from my own PhD supervisor, this wash me but don't get me wet. So how do you measure something, especially a weak signal, trying to amplify this? I'm looking to the director of Ken, probably know what I'm talking about here. At some point, when you look for weak signals, you take out the big magnification glass and you wonder if your method is not actually interfering with what you want to observe. And the last one is really actively ongoing research at the moment, magnesium isotope effects or magnesium oxide isotope effects. So let me quickly revisit Raman spectroscopy. In principle, it's inelastic interaction of light with matter. And so you get the induced polarization, which is essentially the polarizability times the electric field. And we look at this as optical frequencies. So your nu zero would be your excitation frequency. Typically a laser, somewhere in the visible range. Now, what Raman suggested is what happens if your polarizability is not static? What happens if your polarizability oscillates with the vibration of the atomic or ionic species in your sample? And so you get a second contribution here. You get the equilibrium polarizability plus an oscillating part that changes at the speed of the vibrations in the sample, at the frequency of phonons. They are typically 2 orders of magnitude below the frequencies of optical frequencies, sorry. So if you insert this alpha into this equation, you see that you're mixing the frequencies, and you get a first term, which is the elastic Rayleigh term, and you get a second term, this plus here, and the second term, all this series here is the sum term, and the difference term, which is the Raman effect, Stokes and anti-Stokes. And usually I'm discussing that part here. Today, I'm not so much interested in that part. I'm focusing a little bit more on that one here, which is the so-called selection rule. So obviously, because this is a product here, this fellow has to be non-zero to make sure that you get a Raman effect. So this is the selection rule to say, I need a change of polarizability for very small deviations from my equilibrium position. What that means, I'll come to that in a moment with an example. And just as a reminder, if this one is non-zero, then the intensity of my Stokes line, is the one we usually observe, scales with the square of this, because that's actually the electric field intensity with the square of the electric field, so that small change will actually become detectable. With this being said, it's a totally legitimate question. From what amount of this one here being non-zero can we consider it significantly non-zero? Non-zero compared to what? I have to admit, I don't have a good answer. So this is an example. I'm glad I have this animation because usually I do this with my fists in my head. So what you see here is a CO2 carbon dioxide molecule, and I'm going to walk you slowly through different vibrational modes here. So what we'd like to see is whether there is a change of polarizability here for oscillations near the equilibrium position. That would be the equilibrium polarizability. And what you see is in the two extreme states of the oscillation, the molecule is in two symmetric cases. You can basically take the extreme left case when the oxygen pair is to the left, and it's exactly the same configuration, rotated or flipped by 180 degrees as for the oxygen being shifted to the right. So that means you have a symmetric situation here. And regardless how you draw this diagram, if it's symmetric, it has to have a horizontal tangent here. And that's exactly the slope. So that means in this case, the polarizability is zero, or the change of polarizability, sorry, is zero here. And that means this doesn't give you any Raman effect. Now, what we see, this is just complementary information because it's often compared to infrared spectroscopy. You have a change in dipole moment. Your carbon is 4+, oxygen is 2-, and you see that the center of gravity of the positive and negative charges moves left to the right and back and forth. So there is a dipole moment here. Now, there's another mode, which is this one. And from what I just said, you know that the two extreme cases, both oxygen being in and both oxygen being out, they are not related by symmetry. They are different. And that means my situation here, you can, again, draw it as ever you like, is not symmetric. And that means at Q equals 0, there will be a slope which is non-zero. And for that matter, this case here is Raman active. You know, del alpha, the Q at Q equals 0 is non-zero. However, because the center of gravity always stays the same in the middle, there is no dipole moment, it's infrared silent. Now, the last case is the bending. And just from the consideration, I can make this quick. Obviously, the oxygen being in the upper position is symmetrically related to the two oxygen being in the lower position. So this becomes symmetric again, Raman inactive, but because the center of gravity this time moves up and down, it has a dipole moment, infrared effect. The theory is pretty straightforward when you talk about symmetry elements of molecules. And this is point group theory. The situation becomes a little less obvious when you go into crystals. And I'll give you a quick example, and it's also going to show you why I didn't become an artist. I just copied this, and let's imagine you take this chain to be a one-dimensional crystal. And you have the same oscillation. So if you look at this guy here, this would be, if you just look at these three atoms or ions, this would be a Raman active mode. And this one for itself would also be a Raman active mode. The problem is, I didn't do anything. If this one has the two oxygen inbound, this one has the two oxygen outbound. So the translational symmetry means that if you just double the unit cell, you have, again, a symmetric situation through this translational symmetry of that crystal here. And that means that the overall polarizability of your crystal does not change. So this mode is active in a molecule, but it's inactive in a crystal. Because overall, the translational symmetry means that the total polarizability of the sample doesn't change. Now, you can extend this easily to 3 dimensions. And now the question we can ask ourselves, how can we possibly break this inversion symmetry? Good, so let's get started. And the next question is actually, when we break it, how big does it have to become until we can see it? So, sorry, I was a bit quick here for myself. There is a way you can generalize this, what kind of symmetry you need. And the symmetry that is a guarantee that a crystal doesn't have any Raman signature is that you put yourself on any position, on any atom or ion in the crystal. And if you have a perfect inversion symmetry for every location of every atom in the unit cell, then it's for sure Raman silent. Yeah. So strontium titanate is such a case. Perovskite, cubic, and nothing goes on. And I promised you that would be a brute force approach. So we took out, why are we interested in strontium titanate? This is taken from the thesis of Azar. You know that if you change the temperature in strontium titanate, or if you change strain, then you can push the system from one crystallographic structure into another. And you can get interesting properties like ferroelectricity induced in this material, which is a polar order. But you also get different kinds of transitions here. It's not only a polar order, but sometimes you have subunits rotating with respect to each other. So there's quite a bit that can go on in there. And that's an advantage of Raman spectroscopy over, for example, X-ray. X-ray would show you the final result, but Raman spectroscopy can already tell you by the change of vibrational frequency that such a transition is possibly coming, that your system becomes susceptible for this kind of transition, even though it doesn't quite go there yet. So you get a bit more information on that. So we took out, I wish I could say a nail and a hammer, was a nano indenter, and we made these holes into our cubic crystal. They were a few hundred nanometers deep, and this is an AFM image. They have a, I want you to pay attention, they have a triangular shape. So if this material was rubber or some kind of jelly, you would expect a triangular strain field, because that would be the symmetry. What we rather measured when we did a Raman scan, and we used a technique or deviation of Raman spectroscopy to measure strain, we noticed that you get these wing structures. In the middle would be the indentation, and you get these fourfold symmetries. So this picture here is basically the shift of this peak here, of the left one here, as a function of position around. What happens is that during this indentation, we create slide planes. The mechanical stress is accommodated by slipping two crystal planes with respect to each other. There's dislocations building up, and so there's a lot of strain in these areas. But most of all, if there is big strain here or substantial strain here, and there is no strain here, there has to be a strain gradient. There has to be a transition from a lot of strain to no strain. And that strain gradient has to automatically break the inversion symmetry. And that was the moment when we went to see François Legaré and said, can we please do second harmonic generation on these samples? And that was done. And what you see, or there's bad contrast here, my apologies for that. But what you see, we had multiple of these indentations. And in this picture, so I hope your eyes are better adapted than mine to the darkness here. What you see of these dark crosses in the center, always. And where you have the maximum strain, there is no gradient. And that means that's why you have these dark crosses in the middle. But in between, you have for different loads, for different depth of indentation, you have different distributions of second harmonic generation intensity that shows that, yes, around these structures, you have relaxation of strain, you break the inversion symmetry, and your material becomes active in second harmonic generation. That means it also becomes piezoelectric, it also becomes pyroelectric, and so on and so forth. So there is something you could possibly do here. The next point was, can we do this in a little bit less violent way? And instead of poking holes into the sample, can we grow this on a film? And this, what we do here, is a bit like playing with Legos. So we take one Lego layer with the original Legos you buy in a store, and then you would kind of build a second layer of Legos on top with those that you would buy on unofficial websites that are not quite Lego. They look like them, but they're slightly different in size. So you can squeeze them on, but it takes a bit of force because they don't have quite the exact size. So this is the mismatch here that we have. And as we grow this, in this case, this is really, you can think of this as a Lego surface. This is magnesium oxide substrates. These steps are atomically high, so you see them here. And we grow strontium titanate on top. And this strontium titanate has a lot of strain, and it grows beautifully, and it reproduces these steps. So far, so good. So what could possibly go wrong? Well, this could go wrong. So I'll leave you a second to let this sink in. What we have here is a cross-section of our film. So this is a side view across the film. We have the substrate at the bottom, which is our magnesium oxide. And on top, we grow strontium titanate. And in the beginning, strontium titanate will beautifully adapt the lattice parameter. You can think of this like a Velcro, or really like pressing one Lego on the other. And there will be a lot of elastic energy stored in this layer. And you build a second layer on top, and it will still adapt the lattice spacing from the underlying layer. It's epitaxial growth. But with this increasing elastic energy, the total energy of the system diverges with each layer that you build on top. It doesn't go well for very long. So what happens at some point is you create plastic deformations inside your materials, as particular these misfit dislocations here, where you have a larger lattice spacing above than below. And for that matter, you create these voids here where one of the atoms has a lower or possibly higher coordination number, depends on what kind of direction your strain goes. And so you get different electronic properties, but you also get very different mechanical properties here. So this is a zone where relaxation starts. And at some point, this relaxation is over, and you get all these gradients in here. And at some point, you continue just growing your bulk material as if there has never been an interface because it's fully relaxed. So if we look at such a film, we should expect that it should look different from the bulk. And indeed, that's what it is. What you see here is the same spectrum you'd already seen for the bulk crystal in which we poke the holes. Looks, consolation, still the same. But when we look at the thin film of strontium titanate, we actually see quite a number of different peaks. So the spectrum doesn't look the same. And so the question is, what's going on here? And we could use literature to find out what's going on here. So this was still the easy part. We didn't really need to do any kind of simulation here. We could look up what people had already observed in strained strontium titanate. And you see that you have, first of all, a tetragonal distortion. And then you have these polar modes that oscillate here. This is actually carrying a dipole moment. This one carries a smaller dipole here. Tetragonal distortion again. Then you have just the oxygen octahedron oscillating with respect to the inner 4+ ion, and again that deformation here. So you get a couple of peaks that show up, and we understand what they are. The problem is that we have very little control over what is happening where, at which layer thickness. So this is not really a system where you think you have a lot of control in the long term. So we thought, okay, let's go for nanostructures that we have a better control when we produce them, and look how they behave. Maybe one point here, because I was promising a small comment about atomic steps. If you take a very careful look at this picture, this is not a staircase that you would like to walk on. If you see a picture like this from a staircase, you see, oh, you're probably going to triple here. This is a little bit higher than necessary. So that means your step is slightly higher here. This is not a coincidence. This is due to the fact that the diffusion of surface atoms at the edge is slightly different, ever so slightly. It's known as the Ehrlich-Schwirbel barrier, and it comes from a broken symmetry of your system. As long as you stay on a perfectly flat surface, all the surface atoms have symmetry in plane. They just have a slightly different symmetry with respect to the top. So they can probably stick out a little bit further and get some sort of unidirectional expansion. When you come to the edge, the unit cell sitting at the edge has no boundary at all here. It's not sticking anywhere here. So it can actually relax. And so if you look at a step on an atomic surface, there is good reason to believe that it will have a reduced symmetry, and for that matter should be coming with a Raman signature of its own. And we've been chasing this for some time now. I think Mohammed can confirm that it's not trivial. So there is this field of application. For us, it's pretty exciting, because if you can engineer this, then that means that along this edge here, you would have a zone which is maybe 1 or 2 or 3 unit cells wide with different physical properties from the bulk. The edge of these steps would be piezoelectric, or it would provide second harmonic generation. It may provide, well, different electronic properties as well that come with it. So for the moment, that's a system we are pretty excited about, but we're yet to show that it's really different in its optical signature. It's pretty tricky because we don't have necessarily the far field optical resolution to resolve the difference from the step here to the center here. Now, there is a technique that gives us this resolution. And this is tip-enhanced Raman spectroscopy. And that's where I'm also going to bring theory into the game, because that's where things went beyond our reach. So again, this was work done in collaboration with colleagues at NRS in France. And at the moment, Asa is in Munich. So the idea is simple. I'm not going into the details here. You use the tip of an atomic force microscope that you illuminate with your laser, and this tip acts like a local antenna. It produces a very, very bright optical near field that is confined only to the apex, to the very tip itself. And then you can walk around with this tip and basically get an image with a resolution that is way below the diffraction limit of light. So this is optical imaging, which in principle would allow us to measure along the steps. Now, we're not quite there, but I show you some interesting results because it didn't go the way we expected at all. So this is the configuration. We have the strontium titanate surface on platinum. It's not at all as flat as we want you to believe it here. And this is, again, the spectrum of the far field of the film. Now, it took 7 hours to integrate to get this picture. Why? Because it's an optically transparent film, which is only 50 nanometers or so thick. Now, there is not a lot of material that gives you optical scattering. So that's already a pain in the neck to get a signature from that one. When we bring the tip into the proximity, we get this optical near field effect. And within 20 seconds integration time, we get this optical spectrum. Now, what we are hoping for was to get something that looks like this, just brighter. And maybe with a feature more or so. But we didn't at all expect something that different. So the question was, what's going on there? Now, in about 5 or 6 slides from now, I'm going to show you the honest answer of what options are on the table. But I'm going to walk you through the option that we were discussing in first place, which is, this is a Raman signature that we try to interpret in the classical way. And so this was actually the topography. We have the strontium titanate nano island. It is really an optical near field effect because we get the spatial resolution, which is way below 100 nanometers. Every pixel is its own optical spectrum. So it's clearly optical near field. The other news, good news, is we can look into literature and we can again assign the zone of TO1 or TO2, even though they're barely shoulders. There is not a lot in here. You have really to dig into the noise here. But this mode is identified, and this mode is identified, and whatever is going on here is identified. So that's kind of nice, good to know. The problem is that the biggest one is not a Raman peak. And whatever is going on here is not reported. And that was a moment when we talked to Alexander. Actually, we shouted out to him and kind of cried for help. And so Alex introduced us to the software package. I don't know if any here from the theory community is aware of this. It's a software package from an Italian research consortium. It's commercially available. They provide some support for it. And apparently, it gives relatively short computational times because it takes into consideration symmetry elements of molecules or of crystal structures. that you can pick explicitly to then kind of reduce the computational time. So what we essentially do, and at the moment, there were 3 students explicitly trained on that software, Azan, Maria, and recently Lillian, who all had the opportunity to go to Alexander and get the training on the software there. So basically, we define the geometry, whether we have cells that we repeat or whether we have slabs. So like posts that then get repeated with a certain thickness. It's basically a cell with a high anisotropy. And then we choose the boundary condition, either none if we talk about nanoparticles. We can choose periodic 2-dimensional conditions if we try to simulate a thin film, or if we go into periodic toroidal 3-dimensional conditions for solids. And then we choose functionals. And honestly, this is very much done in a way that we pick several. We compare the results, and not having the knowledge which one would be the most appropriate one for scientific reasons, we look for consistency. If the results don't spread too much, we actually get some confidence into the findings. But it's really there is always some scattering. So please take all the numbers with a grain of salt. This is not within a wave number precision, obviously not. And then surprisingly, this can be done on workstations, and it calculates within days or weeks. So would we be interested in getting access to faster computers? Yes. Would we be interested in getting in contact with somebody who has a better understanding on these techniques? Absolutely yes. But before you actually volunteer, let me show you a bit what we can do with that and how far we've already come. So we were calculating this because it was a thin film, or we consider it a thin structure, with a 7 slabs. So this were 7 unit cells. We made it an uneven number to have something in the middle and not be just 3-3 symmetric. And so we calculated, we optimized the geometry in first place, then calculated the vibrational frequencies, then the peak intensities, which is the del alpha del Q squared. And then there is some symmetry related degeneration. So several peaks occur multiple times because they're symmetry related. So this multiplicity actually is also considered automatically. And what came out is that this mode here, the most intense one, is actually infrared mode. It shouldn't be there. It shouldn't be Raman active. Its del alpha del Q is nominally 0. And these modes here, I'm coming to them in a moment, are apparently surface modes. For the moment, this is a self-consistent interpretation. So it's open for discussion, obviously. So this infrared mode corresponds to an anti-phase rotation of the octahedron. So one oxygen layer is rotating like this, the one below like this, it's like a torsion, and it carries some, apparently some dipole moment. So this is the part where things got really exciting for us. So we were for the first time able to calculate surface modes. Everything down here should be perfectly Raman silent due to the continuous translational symmetry. But if we look at these modes on the surface, which by the way also get damped to the inside, we see that there are some modes that actually lack symmetry, that lack inversion symmetry. The surface is by definition breaking inversion symmetry. And so we have these different modes, and they correspond to peaks that we actually do observe. Again, it's self-consistent. The numbers of the peak position kind of add up. They correspond reasonably well. And TERS, this tip-enhanced Raman spectroscopy, has a very low penetration depth. So actually, yes, we are very surface sensitive. So the good news was we see modes that were previously inaccessible by Raman spectroscopy. We're actually able, if this is correct, to see modes of oscillation in the surface. The less comforting news was we also see modes that shouldn't be there. And so this is the open discussion now that is also bringing into what's in literature. So this is option number one I presented to you. So this is dislocation, strain gradients, surfaces, surface effects, surface modes, and so on. There is an option two, which is that if you introduce vacancies, you get local local vibrational modes. They carry some momentum, and so you can go shopping for some additional modes in the Brillouin zone that you would normally not be able to access in the center of the Brillouin zone. The effect that we believe is probably relevant is that when you do this experiment with this gold tip and the optical near field, you get huge electric fields. And these electric fields introduce very high gradients, but even on the scale of a chemical bond, the electric fields are substantial. So these electric fields could very well break the symmetry of a molecule or of a bond, because they are amplified near field electrical fields. And that means that something which was symmetry prohibited before could very well become activated in the presence of a very strong local electric field. So it's like changing the symmetry of your molecule under an applied electric field, or changing the symmetry of your crystal under an applied electric field. So the last option, which is really relatively recent, is that a couple of theoreticians predicted that, well, this kind of spectroscopy you do there is, strictly speaking, not standard Raman spectroscopy. Standard Raman first order means you have one photon interacting with one phonon. And for that matter, you have rules of preservation of momentum, but you have this plasmon resonance sitting on top of your tip, and the plasmon actually kicks in its own momentum. So that in principle, you have a 3-particle process. And for the moment, experimentalists are still shopping for appropriate material systems to verify this, whether there is actually an effect there. So that got us excited about the opportunities of simulating Raman spectra, because it actually gave us some pretty convincing answers to questions we had. And now we try to take this a step further. Wouldn't it be nice to take a material where you don't have a Raman signature, and you just wait and you do something to the sample and see if somehow you can do something to the system that it becomes Raman active? So you just break the symmetry somehow. Whatever signal you will detect is an indication that you reduce the symmetry. And magnesium oxide is a fantastic material. It's chemically stable. It doesn't dissolve in water. It forgives you if you shine full power laser light on it. So it's almost ideal. It's Raman silent. It's only infrared active. It corresponds very much to the chain that I showed you in the first place. It's AB, AB, AB in all directions. Now, why would anybody care? Well, because this is the Raman spectrum of magnesium oxide. It's far from being nothing. And at the moment, the discussion in literature goes into the direction of saying, okay, this is purely second order. What does second order mean? It means you have one photon interacting with 2 phonons. Now, this should be a very, very weak signal, because you have a 3-particle process and the intensity necessarily goes down. You know this from reaction kinetics and chemistry. 3 particles are less likely to react than 2 particles. So how do you explain this? And there is early work on the second order spectra trying to explain this. And I think they're a good starting point. But the question is there maybe something else to it? So this is the phonon dispersion curve. And what I should say, we never really need to calculate the full phonon dispersion curve, because the only thing that really interests us is what's going on in the zone center. All the photons will only interact here. That's because they don't carry any momentum. So Raman spectroscopy would be happening here with these optical phonons, and Brillouin spectroscopy would be happening down here. So what we then did, respectively, what Maria and Alexander did. They calculated magnesium oxide nanoparticles, or things alike that could happen on the surface. You see these shearing modes. This is actually a radial breathing mode, and you have some higher order with a higher frequency. And you see these modes are actually Raman active. You may know this from carbon nanotubes. Radial breathing modes are also Raman active there, but they should be strongly damped if the particles get bigger. But in magnesium oxide nanoparticles, there is good reason to believe that they should be Raman active. Question is, how small do you have to make them until you get there? Experiments that we've done for the moment seem to show that as long as they're 10, 20 nanometers, it's probably still too big. So we need to get to smaller ones. So that could be an interesting idea. And the next thing, this was done on an unrelaxed structure. If we let it relax, the surfaces actually kind of bend outwards. They have a slightly conical shape. I don't know if that's an artifact from the simulation, if that's real. I know that nature then would at some point try to change the Miller indices of surfaces if the center has too much curvature. But if there should be a real ever so small bending of surfaces, that would further reduce the symmetry. And that should give rise to an even larger number of Raman active modes. So that could be an interesting thing to follow up on. Also in terms of simulation, if that's bending of the surfaces is real. But that means dealing with these crystals as if they were macromolecules, just with a high symmetry. And so they have these signatures, and yeah, we treat them kind of like molecules. I just said it. Now, the last thing I'd like to mention here is really the very last item that we started, and that was a coincidence. Who's a physicist in the room here, if I may ask? Okay. So you may have these exciting memories when you were calculating phonon dispersion curves with a piece of paper. You would start with the monoatomic chain. Now, in this case, you have the double atomic chain, one-dimensional, the mass 1, mass 2, mass 1, mass 2. You connect them with springs now, and you would calculate the properties of that chain, and you do it like this, and what you eventually get is the equation for the frequency. I'm not going into the details here. I just felt good to dig this up. Interestingly, magnesium is not a pure isotope. Magnesium has natural isotopes, which are 79% the lightest one, and then 11 and 10% the heavier ones. Now, what happens to that chain if you distribute different masses? It, first of all, will depend on how you distribute them and how do you actually make a proper random distribution. But this has been discussed in terms of mass disorder by Cardona in some recent work. Well, he passed away, I think, but about 15 years ago, and for silicon. And this, I think, was done to show that the silicon peak itself has contributions from this mass disorder, because silicon has not quite the same isotope distribution, but silicon is not a pure isotope either. But silicon is Raman active. Here the question is, would magnesium oxide, or should magnesium oxide be Raman active, because it has this composition of isotopes that eventually break this translational symmetry. If you change the masses by 2, 4, 8%, whatever it is there in detail, you would expect that the total polarizability of that chain is no longer exactly 0. And for that matter, the question is, well, is it sufficiently different from 0 to actually show up in the Raman signal or not? So this is going on at the moment. And so with that, my message I'd like to send here is we have a pretty good tool to make predictions about symmetry properties in materials. We can do this in imaging mode. We can get this with very, very high resolution on surfaces as well. The the biggest challenge for us at the moment is to tell apart what it really is. There is always a number of candidates that could make an effect, and very often we need a numerical backup to know, okay, if this is an oxygen vacancy, for example, where would the optical signature of an oxygen vacancy appear? What would be the mode that would be associated, or the modes associated to the presence of oxygen vacancies, to tell them apart from other effects? So these numerical simulations already gave us some really critical insight, especially for these surface modes. That's why I chose the picture. And maybe to indicate that for the outlook, we are not only interested in structural and vibrational properties. Obviously, as you do these, or as we do these simulations, it's also interesting to look at the electronic properties. Yeah. So yeah, with that, I think I can really shout out loud that we'd love to have more interaction with the theoretical community, and that we have a way to go to see what's feasible these days and what we can do. And yeah, looking forward to common ground there. Thank you very much.
Thank you so much, Andreas, for a wonderful talk. I really enjoyed it. It's really wonderful to see experimental work done with collaboration with theoretical tools, and how we can coordinate the information. It's really nice to see that. Questions? Yes,
sure.
It's about the surface mode.
Yeah.
No, we got something that's solid. There are missing chemical bonds at the place where we cut.
Yes.
And so then
Yes. So you talk about surface reconstruction. Yeah. Yeah. Yeah, totally. Yes. Yeah. So I can be a little bit more specific on that, because we're following up on this. So magnesium oxide, for example, is extremely hydrophilic. Sorry, that's why you use it for sports to dry your hands, because it just sucks up moisture. And there is chemisorbed moisture, which actually translates, for example, to MgOH2. And then there is physisorbed moisture, which is just surface-bound water. And they have a Raman signature, yes. And that's something we can detect. It's a very clear signature if it's really a different chemical molecule or any kind of ligand. Water is a very common ligand. In barium titanate, I think Ifani Chukwu did this in his PhD thesis, we would see the Raman signature of barium carbonate. And the peak of barium carbonate would become ever so bigger as you increase the surface to volume ratio. Yeah, it just becomes more significant if you make smaller particles because you have more surface. So the chemisorbed species are pretty, well, have a pretty clear signature. I think what's way more demanding, and that's a reality, but it's also a scientific discipline which is really in its infancy, is surface reconstruction. That means the surface will react with itself. You know that silicon has these, what is it, 5x5 or 7x7 reconstructions, because you've got these dangling unsaturated bonds, and if nothing else comes, the surface will simply react with itself and create different symmetries. But this is actually part of the hope that we have, that the technique would be able to sense these surface reconstructions. Because otherwise, you would need to go into ultra-high vacuum and then hope that you get sufficient resolution and conclusive data that you actually see this reconstruction by symmetry breaking. The beauty of the Raman spectroscopy, why I think we actually have a bit of an edge over the others, is that we can see if the surface wants to go into this direction. In principle, we can see how specific vibrational frequencies would shift in energy if the structure gets soft with respect to transformation into some specific kind of surface reconstruction. Now, this is dreaming along the road, but I think maybe in 10, 15 years, we're going to have data, if we keep evolving like this, that would actually be indicative of surface reconstruction. Yeah. But yes, surfaces can be complicated.
provide a little bit more of a, I guess, how does it work? How do you actually simulate these modes? Because I'm wondering, why does it take so long? I could do a molecular dynamic simulation of 10,000 atoms.
Yeah. Okay. Yeah. Yeah. Okay. So in principle, it doesn't have to take that long. In principle, if you just look into magnesium dioxide, sorry, magnesium oxide, the unit cell has 2 atoms. It's very easy to define the crystal. You have high degrees of symmetry, and that's pretty straightforward. It goes fast. So it doesn't have to take that long. Things become trickier if you would like to, for example, simulate isotope effects. Because if you want to represent 78, 79%, 11%, and 10%, you should have something in the ballpark of maybe 100 atoms of magnesium to distribute them appropriately. And that means another 100 of oxygen. That means you have 200, and that is your supercell that you reproduce. The same is true for defects. If you look at a misfit dislocation, it relaxes around it. So if you look over which length scale it would usually relax, then you need to make sure that your supercell is large enough to actually cover the range over which it would usually respond. Point effects the same way. So in principle, if it's just the crystal itself, it's pretty fast. It's really simulating deviations from the crystal that become tricky. Yeah, it's DFT based. So in principle, what we do, if you want to get first information on the Raman energy, what you do is you simulate the interatomic bond. You go to the minimum energy, to the equilibrium distance, and you make perturbation theory around that one, harmonic approximations, you get the phonon energy. And so that would be the energy. And to get the intensities, well, you need to calculate the change of electronic polarizability. And that is still classical non-resonant Raman. I don't know, maybe Alexander, you know something about this. Obviously, when you have resonant Raman spectroscopy, like in silicon, where you have an electronic transition coupled to it, things may actually become somewhat more complex. I don't know how that would be properly done, but in principle, you need the interatomic potential and the perturbation around the equilibrium position, and then the change of polarizability, so it has to be DFT. I apologize for the contrast, but actually on the surface, they were all dark. And what happened, and that's something which was a former PhD student of François Legaré, Maxime Rivard, who we brought into the discussion. He actually, I skipped the slide because I was running out of time, but he actually looked up TEM data on dislocations. And what you see is that these slide planes, they actually go down as pyramids into the crystal. And when we focused deeper into the crystal, we saw that the structure, the black area in the middle, actually became larger. So there were like shapes that were actually reflecting the evolution of these slide planes in the depth of the crystal. But I apologize for the image contrast here. You can have a look at the screen in a moment. But these dark squares were always in the center, and it makes sense because that's where you have a maximum of the strain along these slide planes. And if you have a maximum, that means that your gradient becomes 0. Okay. Yeah, fair enough.
Yes, now it is a effect. When you distribute randomly the different masses along the checkpoint, the surface, usually you consider that randomization is actually reestablishing symmetry. So why is this case?
Okay, yeah, it's a good point. So I think it depends on essentially the density of defects. So if you have diluted defects, which are relatively far, then you can calculate your crystal and you just calculate these isotopes as a small perturbation, and they probably fall down the track because they are too small or the contribution is too small. Now, if you look, what is the critical length scale? It should be the phonon propagation length. If the phonon during its propagation doesn't see any isotopes, then crystal is perfect. And you only then would have occasionally one event. But if over the propagation length of the phonon, it would see multiple isotopes, then you get this mixture. So statistically, it is not a symmetry again, because every phonon will see something differently aperiodic. So you average over different aperiodic structure. But what's important is that you have each and every time this broken inversion symmetry. The phonon propagation is in the ballpark of 4 nanometers. In magnesium oxide, you calculate the volume, there is several isotopes within the propagation length of the phonon. And that means that the least thing I would expect, and that's been observed by the way in silicon, is the peak broadens. Yeah. You get peak broadening, you get small peak shifts because you're averaging over these different bonds. But here we talk about a case where it should not be Raman active at all. So the question is, does it become, because you are, in principle, strictly speaking, breaking inversion symmetry. Statistically over big areas, as you said, it gets sort of new randomized periodicity, but with respect to the symmetry of the bonds, it's broken. Yeah.
No questions? In that case, I will ask.
Sure.
So one of my questions is very general. So in catalysis field, we struggle with selectivity of materials. And I am just wondering if these phonon modes can be used to determine selectivity of material. So just, for example, CO2 capture, if you have CO2, nitrogen in that atmosphere, there are so many gases. And one of the biggest challenges is how can we capture just CO2 with this material, and how the vibrational modes of CO2 are, can they determine the activity of the catalyst? Or is it like too far?
So the first point would be that I presume it's metal surfaces.
It can, yes.
No, I guess so.
Yeah.
So in principle, well, CO2 would dissociate, and I'm not sure if it's site specific. What I think could be feasible is to see whether the vibrational frequencies change depending on the orientation of the surface. So for example, comparing two different platinum surfaces and looking at the vibrational frequencies, that's actually something we're looking into at the moment for MgO, actually looking whether the stretching bonds of OH vary depending on the surface, whether it's 100 or 110 magnesium oxide. So the answer is, I would give it a shot, yes. When it comes to the selectivity, I know that it's a different technique, but for CO2 on platinum, what has been done was read oscillation. So instead of looking at, but especially just gives the coverage, so it doesn't really give you the binding properties. No. Good point. So I would give it a shot, yes.
I guess even if we can know the in presence of light, for example, for photocatalysis, how the material changes, how the vibrational modes of material change when we give more electrons at the surface, there are more electrons present, and that might be helpful for chemists to find out if that material could be active based on just the vibrational spectrum. So that would be very, very interesting. Another question I have is about the models. So you talk about defects, dislocation specifically. So how are you incorporating those dislocations in the material?
Not at all, because this goes beyond our computational skill set.
Okay.
I think we could probably define the geometry, but then having this relax, especially these are one-dimensional defects, but you may get some electronic correlation along these lines. We never dared, but that would actually, this is pretty high on my bucket list.
So I don't. My thesis topic was structural and vibrational properties of amorphous titanium dioxide. long time ago. I'm not a physicist anymore. I don't claim to be because after that I started doing chemistry for a long time. So it's very, very interesting, and it's I understand like having a proper dislocation in these structures models is very hard, which is comparable to experimental samples.
You may want to dig up your PhD thesis again, because recently I was a pre-doc from a student of Alia Kakani, Louis Pichon, and he works on the Magnelli phases, so Ti407, which are oxygen deficient, and he would love to learn something about the vibrational signature there.
I didn't do at electronic level, it was molecular dynamics, so
Yeah.
most, but very nice to say that's what I at that time I could not imagine that this such a close comparison could be done between Raman spectroscopy and
There is other activities going on. So I know that Alexander is interested in adsorption studies of molecules on the surface, and to see if you can tell from the Raman signature whether polarization dependent, whether the molecules are lying down or standing up.
Oh, nice.
So in principle, this is something which Federico does. So he can actually measure the height, or basically the tunneling current through the molecules. And depending on the population density or the concentration, in the beginning, they will probably lie down to minimize total anti van der Waals forces. But if you increase the concentration, they all want to bind to the surface, and then they kind of compete. So at some point, they're all going to stand up so that everybody gets this little footprint. And so these are things for which Raman spectroscopy is also evolving. Yeah.
Well, if there are no more questions, let's thank the speaker again. Thank you very much for coming today for the seminar series. I really appreciate it. I don't know if we can all sit in the same room and have a coffee without a mask, but if not, please, I would encourage you to take coffee and snacks on the way up to go to your lab. Because I don't think you can remove mask and be close to each other. So we are still under those regulations. Thank you again. And then the next seminar series would be it's on 6. Do you remember the date, guys? 12. Okay, 12. It's on 12. Thursday, same time. So I hope you guys can join us again. Thank you so much.